Hello, everyone. Have you ever wondered how life expectancy varies across the world? Don't you think major developed countries have a higher life expectancy while others have a lower life expectancy? To answer your questions about life expectancy and its variations across all the countries in the world, my team and I have worked on an analysis. Hi, my name is Yukti, and here are my teammates Lixing and Jising. We are third year mathematics business administration candidates at the University of Waterloo. We have analyzed a dataset obtained from Kaggle.com which contains information about life expectancy, which is our response variable, and schooling, status, rate of polio, and rate of adult mortality of each country. These are the explanatory variables for our analysis. Let us look at the impact of all explanatory variables. For schooling, we see that on average, each additional schooling increases the life expectancy of a country by 0.6 units. For developing status of countries, we see that on average, each developing country has 1.415 years shorter than developed countries. For polio and adult mortality, we see that on average, each additional polio unit and adult mortality increases life expectancy by a negligible amount. In this section, we will look at the variance inflation factor of our explanatory variables. As we can see in the given table, the VIF is reasonable for adult mortality and polio. However, it is a bit high for schooling and status and therefore for their interaction as well. The adjusted R squared value for this setup is 0.8602, which is fairly desirable. We analyzed VIF with the interaction between status and polio. This gave us an adjusted R squared value of 0.8612. However, the VIF goes up to 1300 approximately, which is extremely undesirable. We also analyzed VIF with the interaction between status and adult mortality. This gave us an adjusted R squared value of 0.8625. However, the VIF goes up to 200 approximately, which is again very undesirable. Therefore, we finalize the model with status and schooling with an adjusted R squared of 0.8602.
Before we built the full model, Gini index had 76 missing values and population had 41. You may ask, how do you fill the missing values? I first tried data imputation, which was to predict the variables with missing values by the variables without missing values. However, this method produced very unrealistic predictions. So Yukti and I looked up the World Bank for official data to replace the unrealistic values. We noticed that some countries had inapplicable 2015 data, so we used the values from plus or minus 2 years as a proxy, because we assume that the years around 2015 to be close to the true value. Once the data was cleaned, I used the forward selection to determine the full model. Then I used backward selection to check if the same model is produced. Hepatitis B seemed to be the least significant factor. Maybe we can drop it without affecting our model's fit. To test this hypothesis, I define a function drop var that uses the principle of additional sum of squares to test a reduced model's validity. The resulting f value was around 2.9 and the p-value was 0.09, which is greater than 0.05, the threshold. This means that we can drop the rate of hepatitis B because it is insignificant. Next, we have Lixing to introduce the quadratic term in our model.
After variable reduction, we have 5 variables left in our reduced model. We didn't know whether quadratic trend in x variables exists, so I produced the graph of standard estimated residual spaces each variables to detect that. Based on the graph of all variables, schooling and adult mortality have quadratic trends. As I added a quadratic term for adult mortality, the adjusted R squared increased from 0.847 to 0.857. However, the adjusted R squared dropped after I added schooling squared, so I decided to keep it linear. From the summary of the model, HIV/AIDS and the linear term of adult mortality are no longer significant. So Jinxing ran drop value on the model without those two variables, and the p-value for HIV is 0.416, and that for adult mortality is 0.697, which is higher than our significant threshold, 0.05. After we removed those variables, the adjusted R square increased by 0.001.
Now we're going to be talking about the interaction between our selected variables based on the indicator variable status. We analyzed the interaction of the indicator variable status with polio. The results that we got showed that there was an interaction between status and polio. This was backed up with a p-value of 1.11% using an ANOVA test. While analyzing the indicator variable status with schooling, we observed quite a bit of interaction, which is backed up by a ANOVA test with a p-value of 2.25%. Therefore, the interaction becomes significant as it is under 5%. This can be observed in the plots. Moreover, there seems to be an interaction between status and adult mortality squared from the graph. This is backed up with a p-value of 4.26% using an ANOVA test. We decided to put interaction with schooling in our model because VIF is the lowest and all the three models have showed similar adjusted R square.
Here are the diagnostics plots for our model. We can see that most of the dots on QQ plots follow the straight line, except for those rebellious at both tails, but that's totally acceptable. The standard residuals versus predicted values plot shows no funnel shape in the graphs, which means the graph does not have a non-constant variance, and only about 10 variables are out of the range from -2 to 2, which is close to our expected number 9. And therefore, we do not have to apply the robust standard error. As for the studentized residuals versus index plots, the residuals of the observations are evenly distributed. And the leverage plot shows that we have 3 outliers, but all 3 are only around 0.2, so we decided to keep all the observations. And here is the summary for our model, and our finally adjusted R squared is 0.8602, which is greater than 0.8. That means our model is generally good.
Our model shows that life expectancy is highly correlated with the years of schooling, adult mortality squared, rate of polio, and country status. We had 3 interesting findings. First, once we added the interaction terms, the VIF significantly increased. The model with only schooling's interaction showed a lower VIF than the model with polio's interaction. That means that the former model has variance not inflated as much as the later model, which is more desirable. Secondly, when we put the linear and the quadratic term of adult mortality in the same model, the linear term just became insignificant, and we can use the quadratic term in place of the linear term. Thirdly, income distribution seemed to be an insignificant predictor, perhaps that the mortality tends to be lower in the economies with more equal distribution of income. One limitation with our study was that the impact of adult mortality and polio seemed to be really weak. That makes it is questionable to whether this model is a good prediction of life expectancy. Finally, let's hope that less developed countries have more accessible healthcare, better nutrition, and more affordable education.